Hello, my name is Monica, and in this video I'm going to show you an example of Gamal digital signature. So as you probably know, we always use digital signatures together with hash functions. So when we have message M, we compute hash of this message. Now this hash should be computed with secure cryptographic hash function, for example, SHA-3. If you want it to be secure, this hash computed for this message should be at least 256 bits long. If you want to have post-quantum security, it should have at least 512 bits. So actually, we never sign entire message. We sign just the hash of this message. So we do that because of two reasons. So the first reason is that we want our signature to be kind of short, something attached to our message. So imagine if you would say, if you want to send huge video, right? If you don't work with hash, then your signature will be also a kind of big. So you just want to compute the hash of the video and sign only this hash. If this is cryptographic secure hash function, then this is very secure. In fact, more secure than using signatures without hash functions. So we compute signatures of the hash on the hashes. Okay? And then when we send message together with signature computed this way. When we work with Gamal digital signature, we can do computations in multiplicative group of integers modulo p. Okay, so we have multiplicative group ZP. So what we have here in this group, well, we have numbers from 1 to p minus 1. So basically we have remainders modulo p, but please notice that 0 is not there. Now the operation that we use is just multiplication modulo p. Now there is something that we call generators of the group. So if we have some kind of number that can generate all numbers in this group, then we call this specific number generator of the entire group. So let's say that we have some small group. We will use number 5 here. So in this group, we have elements 1, 2, 3, and 4. Now, if I will take number G, generator, it's in fact generator, let's say 2. Now we compute 2 to power 0 modulo 5. This is 1. 2 to power 1 modulo 5. We have 2. 2 to power 2 square modulo 5. That gives us 4. And 2 to power 3 modulo 5. This is 3. So you see, we are able to generate all elements in this group. So we have 1 here, we have 2, we have 3, and we have 4. It doesn't always happen for some groups. Some numbers do not generate entire group. Okay, if you want to learn more about multiplicative groups of integers modulo p, you can see my other video with some short Python live coding. So for Gamal digital signature, we need to generate private and public key of the person who is going to use the signature. So first thing, we generate keys. So we choose large prime number. Let's say P. Then we choose a generator of large order subgroup. Large order subgroup, it means that we want this generator to generate a lot of elements in this group, like at least half. Choose a generator, let's call this generator G. And then we have, we choose, now why we choose, so actually we don't choose, we should use pseudo-random generator or true random generator in order to choose our private key. Small letter A. Okay, and then we compute public key. Uppercase A, so we compute it as G to power A, everything modulo P. So we have secret and we have public key. So of course, on paper, we can just do some kind of like a toy example of this signature. So I'm going to use P equal 83. Then G that I want to use, G is equal 7. I decided to use this one because it generates subgroup of order 41. So this is good size subgroup because we have half elements of the entire group. Then let's say that I generated secret key A equal 15, and we can compute our public key. So that will be 7 to power 15, everything modulo 83. So that gives us A equal 31. Now, if Alice wants to send a message and sign it, what she should do, she should publish uppercase A, her public key, so that everybody can see it in order to verify her signature. Okay, so we have those public. We have this public key. So what is public? G is public, P is public, and uppercase A. Now let's say that we have Alice here. And we have Bob. And Alice, she wants to send the message to Bob. Let's say that this is 25 and hash of this message M is equal 18. Okay, so let's just assume this is given. And remember that Alice, she keeps her secret key A for herself. So this A was equal 15. Only Alice knows this number. So actually, her entire signature, the thing that only she can sign her messages, it depends from this one number. Of course, it will be much bigger if you use bigger group. And those numbers here are public. So here we have this. We decided to use G equal 7. P, this is 83. And we computed A as 31. So now, how does it look? What we have to do in order to sign this message? So there are 4 steps first step is we choose a secret number, not key. We choose a secret number K. Now, it has to be chosen in such a way that greatest common divisor of K and P minus 1 must be 1. Why we need it? So in the next step, we are going to compute inverse of K. And in order for this inverse of K to exist, we need this greatest common divisor of K and P minus 1 to be 1. Okay, so this is first step. Now in the next step, we compute something that we call R. And this is just G to power K modulo P. In third step, we compute inverse of this secret random K. So you can compute it either with extended Euclidean algorithm, or you can use Euler's theorem. It's in my other video how to do that. So basically this number, this inverse of K, it has to be some kind of number that when we multiply this number by K, and then we do modulo P minus 1, this should give us 1. Okay? So we are looking for such number that satisfies this property. Then in the fourth step, we compute something that we call uppercase S. And this S is computed as inverse of K times hash of message M minus secret key A times R that we just computed, and everything is modulo P minus 1. Okay, so those are those 4 steps to compute signature. What is this signature? So Alice sends to Bob message M, and our signature, this is pair of 2 numbers, we send R and S. R and S, this is our signature for message M. Now, to verify, Bob computes G to power H of M, and he checks if this is congruent to A to power R, R to power S, everything modulo P. Okay, so if this formula is true, if left side is congruent to the right side, then it means that signature is valid. This is really Alice who sent this message, and this message was not changed during transmission. Okay, let's see it now with numbers. So about this secret K, so this K we generated every time we sign new message. Okay, so we have the secret key A that we don't tell to anybody. We keep it secret just for us because we need it to sign all different messages. And this K is generated every time we sign new documents. Okay, so first step, I decided to use, let's say I pre-computed a pre-generated K equals 71. Now in the second step, let's say that of course, it satisfies this property. So the greatest common divisor of 71 and 82 is 1. So everything is okay here. Then we compute R. So G, this is 7, to power K, 71, everything modulo P minus P, 83. That gives us 48. In the third step, this video is not about it, so in the third step we compute inverse of 71 in ring modulo p minus 1. So we are looking for this such number that this number, let's say like this number x times 71 modulo 82 is 1. So this x, so the inverse of k, this is in our case 67. And fourth step is we compute s. So s is equal 67. Hash of message, so we assumed it's 18. Minus a, the secret key that Alice keeps for herself. 15 times 48. And everything is modulo p minus 1, so 82. That gives us 34. So Alice sends message to Bob. This message is 25, together with signature R, 48, and S, 34. Okay, so she sends this to Bob. I don't have much space to verify the signature, but maybe I will fit in this small space here, or I can actually clean this a little bit. So I will have more space here. Okay, so what Bob computes, he computes left side, so we have G is 7, to power hash of M, 18. Now everything modulo 83. This gives us 9. And he computes the right side, so uppercase A, right? This is Alice's public A. So this is 31 to power R, uppercase R. He just received it as part of the signature, so this is 48 times 48 to power 34, second part of the signature, everything modulo 83. And in fact, if you will compute it, you will see that this is also 9. So he checks that first part of the computations and second part of the computations, they give the same result. So her signature is verified. Oh, thank you very much for watching and have a good one.